Dalton's law states that the total pressure of the mixed gas is the sum of the pressures of the individual gases in the mixture. Okay, so however many gases there are in the mixture, each gas contributes to the overall pressure. And I think this will make more sense to you by looking at an example problem. If we think about air, air is made up of nitrogen and oxygen and other gases, but it's mostly nitrogen and oxygen. About 99% of it is nitrogen and oxygen. So if we have those gases, if the pressure in the room is 101.325 kilopascals, and the partial pressure of nitrogen is 79.03 kilopascals, and the partial pressure of the other gases is 101 kilopascals, what's the partial pressure of oxygen? And remember, air is the kind of total mixture, and so we're saying that the pressure of air, the full mixture, is going to equal the pressure due to nitrogen plus the pressure due to oxygen plus the pressure due to everything else. We're told that the total pressure is 101.325 kilopascals. And that's going to equal our pressure due to nitrogen, which is 79.03 kilopascals. I don't know the pressure due to oxygen, that's what I'm solving for, but I do know that the pressure of everything else is 1.01 kilopascals. If I add, kind of combining like terms here, I get 80.04 kilopascals plus my pressure of oxygen will equal my total pressure of 101.325 kilopascals. And so all I need to do now is subtract 80.04 from both sides of the equation. So that I can get the partial pressure of oxygen all by itself on one side. Now, according to my calculator, this subtraction problem gets me the answer of 21.285. Let me write it over here, 21.285. However, the thousandths place is not significant because I don't have a thousandths place measurement here. Therefore, I need to round my value off at 21.29, and I have kilopascals for my units. And this is my partial pressure of oxygen. So it's a fairly straightforward concept, but it's going to come into play for the next thing that we learn. And the next thing we're learning is how to collect gases by water displacement. So if you ever have a system that's producing gas, you can collect that gas over water by using water displacement. Basically, you take a graduated cylinder or some other kind of measuring tube, fill it with liquid, and turn it upside down in a container of water. Now, due to kind of atmospheric pressure, that water will stay inside of the tube and until you pump gas into the graduated cylinder and you collect the gas here, and as the gas goes into the tube, water flows out of the tube. So this is a way that you can collect gas. But not all of the gas you collect is, in this example, oxygen gas. Because as the gas bubbles through the liquid, it picks up water vapor along the way. And depending on the temperature of the room, you can pick up quite a lot of water vapor along the way. So it's important to correct for that factor because you're not just collecting your target gas, you are collecting water as well. So we need to find a way to account for that water vapor that is mixed in with the gas that we're trying to collect, where the total pressure, the pressure of the room, equals the partial pressure due to the water vapor plus the partial pressure due to the gas that we're actually trying to collect. Now, this partial pressure of due to water vapor, we can get that value using a water vapor pressure table. What you do is you look up the temperature of the room, which is typically going to be between kind of 15 and 25 degrees Celsius, which is why there are so many temperature points between here, so you can get a fairly accurate reading. And so our room might be 20 degrees Celsius. And then you find out what the partial pressure of water vapor is at that temperature. Not surprisingly, the closer you are to the boiling point of water, the higher the partial pressure of water is in that situation. So we can use this information to do calculations to help us find out how much of our target gas did we actually collect. So let's do a sample problem. Oxygen gas from the decomposition of potassium chlorate was collected by water displacement. The barometric pressure and the temperature during the experiment were 731 torr and 20 degrees Celsius respectively. What was the partial pressure of the oxygen collected? So the total pressure in the room is 731 torr, and remember that torr is the same as millimeters of mercury. And the temperature of the room is 20 degrees Celsius. So let's go back and look at that table. The partial pressure due to water at 20 degrees Celsius will be 17.5 millimeters of mercury. So the total pressure of the room is going to equal the partial pressure due to water plus the pressure due to this oxygen gas that we're collecting. So 731.0 equals our 17.5 from this previous table plus this pressure of oxygen that we're trying to calculate. So if I subtract 17.5 from both sides of the equation, I will get 713.5 in millimeters of mercury. mmHg is my partial pressure of oxygen. So these calculations are relatively straightforward, but you do need to understand how to read a water vapor pressure table like this one, and you'll do practice homeworks with that. I hope this helped.